All right, let's get going here. If the PowerPoint will work with me. All right, change in motion, here we go. So a force, basically any force can cause a change in motion. In some cases, it's as simple as changing the direction. In other cases, it's stopping it and reversing it. So we'll talk about all of those. Force is measured in newtons, a little different. So we'll talk about what that means. Gravity. So gravity and magnetism both act at a distance. We'll talk later on in this chapter about section 4 about friction, which is direct in contact. So force diagrams is what you'll pretty much use, and you've started to see me use them already on drawing arrows and which things go and which way they have to be resultant. So this is one things that always will get you guys caught up is magnitude and direction. Even in chapter 3, when they sat there and said, well, what was the magnitude of the resultant vector? You need basically the hypotenuse and the angle. So that's why it's a vector quantity almost always. Vector quantities are shown in diagrams, and free body diagrams only shows the force itself. So a little bit different there between a vector. Example, here's a lovely picture, high quality. Force diagram shows all the situation, what's going to happen, what's going to result. Now, in a free body diagram, I don't care about the wall, I just care about what's happening to the car. So the wall itself is disappeared in a free body diagram. Again, I'm only concerned about what's happening in the car, so that's what's the difference. Yeah, we will pull lots of things up inclined. I'm not going to worry about that demonstration right now. So the situation is this. Imagine a book sitting on the desk. If a book is sitting on your desk, at some point in time, at a certain angle, certain tilt, it's going to slide off the desk. Why? Short version, just like your body. If you stand on an angle, at some point in time, force of gravity is going to try and pull you down the hill. Pulls you down the hill, it's acting in the x direction. It's also acting in the y direction, and that's what the big part of chapter 4 is figuring out where does the forces lead and how do we calculate them. So let's jump right in. Newton's first law, object at rest remains at rest, continues in a straight line until acted on by an outside force. Basically, it's going to keep doing what it's doing. So there you go. Car on the ground, car forward resistance, it ain't moving. Now, what if I said it was moving, the force forward was being matched by the force backwards? Example, if you're driving and your car is putting out 115 horsepower going forward, couldn't you figure out the resistance of 115 backwards by air and by friction of the tires? Yes. That just means the sum of the forces is 0. Doesn't mean the car is not moving, as it says right there. It says the constant velocity. Guess what? Constant velocity, not speeding up, not slowing down, is going to be something that's important. So here we go. Derek leaves his physics book on top of a drafting table, inclined at 35 degrees. There's the free body diagram. Notice they're starting to use the subscript, the force of the table on the book. Friction is holding the book up. Force of gravity is acting straight down as it will. Now, the hardest part is we have to add these calculations together, or add the forces together and figure out, okay, what? Is it moving or is it not? So we start by breaking it apart. Given stuff, come on. Whoa. This is where X and Y starts to break down. If you notice, the force of the friction is acting 11 newtons straight up the XY plane. We've tilted the XY plane because it makes life easier. We're going to break apart the force due to gravity into the X and Y force. This will be the hardest part. So if you look, we make a triangle. The angle of 35 degrees, we have to calculate what that is. So by using our triangles, oh look, 35, 90, that angle has to be 55 degrees. So now we have to sit there and say, okay, how much force is being pulled down versus how much force is going down in the y? This is a use of your cosine and sine again. Force due to gravity in the x is Fg times cosine of theta. Force of gravity in the y is sine of theta. That right there, this and this, these two equations are the biggest part. If you can do this over and over and over again, should be good to go. Okay, we'll talk about specifics on why this is important. But the idea is, okay, if you think about it, force due to gravity is going straight down, and now we're going to make it go to the right. So then that 18 newtons is holding that book to the gravity, or to the desk, excuse me. Now, if you look back, wait, our picture says it's 18 newtons. The table is pushing out of the table with 18 newtons. Force of the gravity is 18. Well, that's kind of convenient, because if it's full 18 to 18, that cancels to 0. Is the book sinking into the table? No. Is it flying off the table? No. So that's kind of convenient. The math actually works. So when we break it down, now we have 13 going to the right and 11 going to the left. Uh-oh. Sorry, sarcastic day. Happens. And there we go. For the y direction, it's not flying off the table, but for the x direction, we have 2 newtons. The sum of the forces in the x direction is 2 newtons. Guess which way it's going? I know, right? Look at that. Force 2 newtons. Accelerates in the x direction, or as we have drawn it, to the right. That is the hardest part about section 2. Okay, take a second. I'm going to do another problem in another video, but we're going to get there here in a minute. You don't have to watch it, but you need to make certain you take the chapter 4 A and B practice or check on learning. Don't forget.